Okay, so I'm Matthew Reevy,
And I'm Atticus Clausen.
and this is our tech project, the Automated Bartending System.
In this presentation, we'll be talking about pathway analysis, project developments and iterative improvements, market scope, legal considerations and conformance, as well as project design and creation.
Okay, so our project objective is to create an automated drinking system that specializes in alcoholic beverages, which will take direction from different ordering systems with the goal of correctly and accurately pouring a drink. Our initial goal for this project was to have it replace bartenders, or at the very least be another form of ordering alcohol within bars and restaurants. It would allow people to order through an HMI menu screen or through a wireless option such as Bluetooth. Due to legal obligations, we quickly found that we had to change the overall goal of our project from replacing bartenders in bars and restaurants to being more of a home device that can be controlled and maintained completely by the owner.
These are the four solution pathways that we have came up with to try and solve our problem. First was the Arduino, which would be used as a microcontroller. From our research, we found that it was a very cost-effective option, although neither of us had ever coded using the system before. The advantage of this system is that there is a lot of research and tutorials online to help us through any struggles we may have. Second is the PLC, obviously a very expensive part to use, but very familiar and reliable as we have spent multiple semesters learning how to use them. Third is the analog control, again, a high cost, not as much as the PLC, but still expensive. This system is very reliable as well as easy to troubleshoot, but not the best option for the design of our project. Lastly is the microprocessor, which is very low cost, similar to the Arduino, but is also extremely capable with proper code and program implementation. As we are not familiar with this system, this option was discarded.
So this is the revised decision matrix. Initially, our decision matrix rated the four pathways on a scale from 1 to 4, but as the differences between the devices could be so drastic, for example, the cost of a PLC compared to a microcontroller, we decided to redo the matrix with a rating system of 1 to 10, and these were some of our results. As you can see, the PLC compared to the Arduino is the complete opposite, 1 to 10. Reliability and familiarity, PLC is number 1 for both of those. Ease of use, definitely the Arduino, just because of all of the research we have access to it. So the Arduino is the lowest on all 4 of the scales, and the PLC is actually the highest on all 4.
Upon analysis, we decided the microcontroller was our best solution pathway as it is simple and easy to use. It's very cost effective, compatible with all of our electronic devices, and easy to troubleshoot using the serial monitor function within the Arduino IDE. This system is easy to program, and there is a copious amount of research at our disposal to help assist us should we run into problems. We want our project to be applicable in a residential environment, having it as an addition in a home bar or as a countertop device. We wanted to make it similar to the Keurig device while being sized appropriately for residential use and very affordable. After doing research, we found 4 different competitive brands that are producing a similar device to ours, but each one has 1 or more major flaws. The Soma bar never got off the ground and their Kickstarter campaign failed. The Barbotics system is pre-order only. While it does have a lot of similar applications as ours, they are not capable of pumping carbonated drinks with their system. This severely limits drink variety of the system as a whole. The Monsieur is a $3,000 product and utilizes only 4 pumps, which is already half as many pumps as we have for an incredibly large price. And lastly, the Maker Shaker. A cool concept, but quite irrational. The system uses multiple KUKA-style robots to grip the cup, add alcohol, and mix the drink. The idea is interesting, but not practical or marketable at all. We created our device to be financially affordable and not require insulation or a large amount of counter space. Our system is simple, intuitive, and marketable.
So our initial idea was to have a countertop drink dispensing system with the ability to mix 37 different drinks, 3 alcohols and 4 mixes. We wanted it to have an HMI and a Bluetooth controllability for a manual and wireless menu system, a way to switch our device between free mode and payment mode for certain applications, and a fingerprint account verification and payment processing, which would identify a user and allow them to pay for their drinks while just swiping their finger. What we actually ended up doing was slightly different. We still had the ability to mix the 37 different drinks, the 3 alcohols, and 4 mixes. We still have an HMI and Bluetooth controllability for a manual and wireless menu system. But because of the legal obligations we had to follow, which we will discuss in a later slide, we got rid of the payment mode and free mode and added in an RFID card reader, which adds some safety applications to our system, as well as adding an e-stop directly connected to our pumps in case of overflow or any other emergency. These are some of the laws that we had to avoid at the beginning of our project and why we strayed from our initial idea. First, it's illegal to profit from the sale of goods without taxation. Second, it's illegal to sell and knowingly allow minors and intoxicated guests alcohol. And lastly, it's illegal to sell alcohol directly from a vending machine. This is how we altered our project in order to appease to these laws. The machine is designed to simplify drink making, not to actually replace a bartender. No actual sale of alcohol occurs. The owners must stock the machine themselves, and they are able to gift drinks as they choose. All reasonable security measures have been implemented to avoid unwanted and illegal usage. This relates to our RFID card reader. We created a system that only allows certain people to use our device. Any card with a scan function has a certain 8-digit code that is unique to that card. This way, when the card is scanned, we can take the card number and program it into our code to allow that person access to the machine. This way, someone can't just use their own card and hope it works. In addition to that, the RFID card also allows us to place a limit on the individual's card to regulate access and prevent overusage.
The system produced cost quite a bit to make. Unfortunately, a lot of this was due to an ordering of the wrong parts and their requisite reordering. Overall, the system ends up being just under $500. The majority of the system price is found in the air and liquid pumps. The pumping system costs over $100. System hardware and associated materials also represent a large portion of the project cost, while electronics were found to be rather inexpensive.
The electrical layout of our system follows this illustrated path. It travels from the AC power, changing into the DC power supply, then flows to the voltage regulator, which steps down the voltage to the necessary amount in order to power the Arduino, which in turn powers the control side of the relays. Going back up to the DC power supply, it also connects to the power side of the relays, which in turn powers the pumps when initiated. Looking at the images on the right, the first drawing is the Arduino Mega and all of its connections stemming out, including the joystick, HMI, RFID reader, the relay connections, push buttons, and the Bluetooth connection. Drawing number 2 outlines the specific Bluetooth connection, the VCC and ground, the RX and TX connections. Drawing number 3 outlines the HMI connections, the SCL and SDA pins, as well as the VCC and ground. And lastly, drawing number 4 allows the RFID connections, the SCK and SDA pins, along with the MISO and MOSI connections. Each individual drawing has their own pinouts routed to the Arduino in image number 1.
The hardware layout within the system was primarily dependent upon power supply and pump location. It was found that the pumping system and relays worked most effectively if located at the rear of the system. This location meant that the system, plumbing, and conductor length was as minimal as possible. The power supply also required a large amount of system space, with much of the circuitry being mapped in allowance to it. As the system is used in conjunction with liquids, consideration for water management and spills were made. This meant mounting all electronics as remotely and as contained as feasible. An Android-based mobile application was created in conjunction with the bartending system. The primary function of the application is to send Bluetooth data to the system, which in turn will create a requested drink. As the system is capable of receiving orders both locally and remotely, implementation of cup presence sensor code is necessary. This code ensures that no drink will be made without a cup present. As currently pictured, the application is made up of 3 individual screens. Upon startup, users will be directed to screen 1, in which a scrollable Bluetooth device selection menu exists. The user will choose the system's HC05 Bluetooth module in this screen. Once connected, users are routed to screen 2. This screen is used to select a drink from the scrollable drink list, shop menu, or to select a random drink. When a drink is selected, associated sizing options and drink information is displayed on screen 3. From here, a user is able to return to the drink selection list or to continue with their order. It is important to note that a password is required to access the system's Bluetooth module. This integrates access control into the system in order to prevent unauthorized access.
Initially, the system will look for a drink request from the ordering menu. If a drink is requested, the system will then check if a cup is present as well as verify identity, which is just making sure someone has scanned an authorized card. If a drink is not requested, the pathway will revert back to the top and continue looking for a drink request. If the cup is present and the identity verified, the system will either allow a drink to be made and display a thank you message, or if the cup or card is not verified, the drink will be denied and a denial message will appear on the HMI. After both options, the system will revert back to the top and begin looking for a drink request again. We performed several stages of testing throughout the project. The first was connecting the circuit, ensuring every individual part works by themselves, and testing the additions as the circuit grew larger and larger. Phase 2 was testing the code by running the system with the pumps attached, making sure the relays initiated the pumps and they were on for the programmed amount of time. At this point, the bottles were not prepared or routed into our system, therefore no actual drink had been made. Phase 3 was attaching the bottles and filling them with the appropriate liquid in order to test every single combination possible and ensuring that they passed the allowed tolerance. We set up a tolerance value of 0.5 ounces for the mix and 0.1 ounces for the alcohol. The reason the mix is slightly higher compared to the alcohol is due to the air pumps. As the volume of liquid decreases in the carbonated drinks, the air pumps take slightly longer to push the liquid up through the tubing, causing a slight delay in any drink that requires Coke or ginger ale when their volume is low. Unfortunately, there is not much we can do about this fact, but overall, all the time it takes to fill the tubing at maximum volume compared to the lowest volume is under a second, so there is no large discrepancy between the two volumes, and our tolerance remains intact. The following table is the result of our initial testing during the third phase of our tests. To ensure that every drink passed the allowed tolerance, we went through every type of drink, every size of drink, and marked down whether or not they were within the allowed tolerance. As you can see from the results, many of drinks were not within the allowed tolerance and many drinks were, showing that our code had to be altered to ensure correct times for all of the drinks. The results in this table show all of the altered values and how far away each drink is from the 12-ounce norm. After altering the code for all of the drinks that did not pass the Phase 3 testing, it was found that no drink was out of our allowed tolerance of 0.5 ounces for mix and 0.1 ounces for alcohol.
The next few slides will cover the video presentation of our project. The videos will cover both the local and remote ordering process, as well as an example of an accepted drink, a denied drink, a random drink, and emergency stop functionality. The figures below better illustrate application of the HMI within the system, as the following videos do not display the LCD screen as intended. What we're looking at here in this blue flashing light is the Bluetooth module of the system. As it's flashing right now, that means that there is no device connected to it. When we go over to the app screen, the first screen you're presented with is the Bluetooth connection screen. We'll scroll down to the HC05, which is our device. When I click this, you'll see the blue flashing light change. Once it changes to flashing at a slower pace, that means it's connected. We'll then go back to the app menu. You have a scrollable drink list here, as well as a shot menu, and then the rules and confirmation for the random drink. Say we want one shot of rum. We'll click the rum button. It tells you a little bit of information about your drink, and then we can order it from the phone remotely. Okay, in order to make a drink with the system, two main things have to happen. Number one, a card has to be scanned, which has been done. And number two, a drink has to be under the nozzle over top of the photoresistor, which acts as a cup presence sensor. So when we go to order a drink, even though the card has been scanned, it won't verify it because there is no cup under the nozzle.
We're going to scan it once, and we're going to show that the drink size is 1, card balance 93. We're going to scan it a second time, making it a double, card balance 92 left. This is the double button here. We're going to scroll down to a Cuba Libre. Our red solo is on our light sensor here, and when we press the double, it'll work. Right there, it's a drink.
3, 2, 1.
Okay, so we're going to demonstrate our manual ordering system again. So this time we're going to make a triple. So scan our card 3 times. So 1, 2, see the drink size 2, and now drink size 3 with the balance 88. Place our cup over the sensor here. Ensure that our pumps are on. We scroll down to the Ryan Coke right there, and then we just hit the triple, and it should work. And there's the cup.
1.
Okay, so the second or third demonstration actually of the manual ordering system. This time we're going to do a shot instead of a mixed drink. So again, scan for, we're going to do a double shot this time. And we're going to scroll down to the shots. I'm going to do a shot of whiskey, a double shot of whiskey. Place our cup over the sensor, pumps are on, and we hit the double button. And it goes. And so here's the double shot.
Our system also has an e-stop built into the top, so if anything were to go wrong, you can automatically shut drink making process off. As it is right now, it's off. When we turn it on, this enables the system as a whole. If there's a drink under and the card is scanned as usual, we can order a drink. We'll come over here, order the drink that we want, and if anything goes wrong, we can shut it off with the e-stop. Our product also has random drink functionality built into it, so if a cup is present under the nozzle and a card is scanned twice, we go over to the LCD, down to a random drink. This is the random drink button. Once pressed, a random drink will be made out of 2 ounces of random combination of all the drinks. The size is 2 ounces each to allow for a shot size drink.